in this lesson, we are going to discuss the representation of a complex number in a complex plane. So now my axis, instead of calling them x and y axis, I have an Argand diagram where I call them real and imaginary axis. So a number z, x, which is x plus iy, this is the Cartesian form of representation of a complex number, where x comma y are real numbers and I is square root of -1. On the complex plane, this can be represented as a number which has x units on the real axis and y units on the imaginary axis, and that's what the number x plus iy looks like. So let's take some examples and understand them and know more details about the representation. So the number is z is equal to 3 plus 4i. So it's very evident that 3 is the real part and 4 is the imaginary part, and the number would be 3 units on the real axis. So I'll take origin as my reference and I'll count 3 units on the real axis and 4 units on the imaginary axis. So this is my I-axis and this is my real axis, and that's why my number is. And the arrow shows the direction, the directed segment going from the origin to the complex number. So this particular complex number is at a distance of, so if I want to think about how far the complex number is from the origin, I represent it as mod of z, and is also called the modulus or the magnitude of the complex number, and is given by square root of the real part square plus the imaginary part square. We had already discussed this in the previous video, but just to remind you, it is simply Pythagorean theorem which is being used in the complex domain, because all my rules of algebra and mathematical principles that I've learned are still applicable. Because I'm in complex plane doesn't change anything. In fact, all real numbers are a part of the complex numbers. So everything that I worked with real numbers is also applicable here. And it is also at an angle of theta, which is tan inverse of 4 by 3, and we call this the argument of the complex number. Correct? This is how so while we are representing it using the Cartesian form in the complex plane, we also need to know that these are important parameters associated with that. Similarly, if I have to think of a number, let's take an example of a complex number z2, which is 5 minus 5 minus 2i. Minus 5 minus 2i. There is a negative real part and a negative imaginary part. Same like our quadrants, which used to work in first, second, third, fourth quadrant. We similarly have a relation. So if the right side of the origin is real positive or real positive numbers, then the left side is negative real numbers. On the above the origin or above the real axis is positive imaginary numbers, and below the real axis is the negative imaginary number. So minus 5 minus 2i will be 5 units on the left of the origin and 2 units below the origin, and that's where my number minus 5 minus 2i is. What about the modulus of this number? Modulus is going to be square root of real part square plus the imaginary part square. Remember, modulus is never negative because I'm simply looking at the distance. Distance doesn't have any direction, so it is not negative. And it doesn't matter whether it's minus 5 or plus 5, the square is going to be positive only. So 25 plus 4 square root of 29. Even if I had a number 5 plus 2i, the modulus would have been the same. So it only depends on the magnitude of real part and magnitude of the imaginary part which is impacting the modulus. What about the argument here? If you look here, tan inverse of minus 2 upon minus 5. Well, I would not be able to distinguish whether this, unless I knew the Cartesian form, I don't know whether it's tan inverse of 2 by 5 or if it's minus 2 upon minus 5. That's why sometimes knowing the Cartesian form is useful to know in which quadrant it is. Simply, if I give you the argument here, both the modulus and the argument are positive, and you may mistake it to be in the first quadrant, So both formats have their own use in representation. Something interesting that I would like to show you in the complex plane is a number z. Let me use the same example, 3 plus 4i is here. This is 3 plus 4i. Its conjugate, which is represented as z bar or z dash or sometimes z star. There are various notations that are used in different books, but the meaning is the same. So if I need to write the complex conjugate, all I do is the sign of the imaginary part is changed. So the distance from the origin will remain the same. The real part will remain the same, just that the imaginary part would now become minus. So if this is z, this is z bar. Then what about minus z? Well, minus z is somewhere here. Minus z has the negative real part and the negative imaginary part. Minus z is minus 3 minus 4i. Both the real and the imaginary part are changing signs, and then minus z bar, what is the conjugate of minus z, is going to be a mirror image above the x-axis of that number. So it's going to be minus 3 plus 4i. That is minus z bar, right? So that's the meaning of conjugates and how they look in terms with respect to each other. If you see the modulus of z, z bar, minus z and minus z bar, all are same, correct? However, their orientation, which means their argument, is what is going to tell you in which quadrant they are and how would they be. So they are symmetric so z and z bar are symmetric about the x-axis, whereas z and minus z are symmetric about the origin. So this is what is the complex plane and how numbers are represented. If you see, there is a huge resemblance between complex numbers and 2D vectors. So you may have a question on why are we using complex numbers if we already have 2D vectors. The biggest help of 2D complex numbers is that multiplication operation and division operation is very different. Multiplication in vectors have two kinds of methods: a dot product which results in a scalar and a cross product which results in a vector. But for complex numbers, multiplication and division will result in another complex number. Okay, and that's what we want. We don't want the form to change to something else. That is the reason we need complex numbers for making sure that multiplication and division operations are done as per the regular arithmetic rules, which is not the case with 2D vectors. So that justifies the use of complex numbers, despite till now you will see a lot of similarity between vectors and complex numbers. But when we get into the operations and some of the proofs, you will realize that complex numbers have their own use.